Hello, ladies and gentlemen. This is Mr. Green. This is another one in my recording series on geometry. Yes, geometry. So, what are we looking at today? We're into Unit 3. And in Unit 3, it starts talking about polygons. And of course, there's the very old joke that I have to tell you. What did the pirate say when the bird flew away? Polygon. Of course. Everyone knows that joke. Yuck, 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 yuck. Okay, so when we talk about polygons, there's several different types of polygons we talk about. We talk about octagons, and we talk about triangles, and things like that. When we talk about the word regular, regular means that all the angles and all the sides are all the same. So if I were looking at these objects down here, and which one is the regular octagon, it would be this one, because all the sides are all marked as being equal to each other, and I see 8 different sides. Well, that combined with the fact that the other two are triangles, that doesn't help. That helps matters here a little bit. Octagon means 8, 8 different sides. Octagon. Okay. So the next two here say isosceles triangle and right scalene triangle. Well, isosceles might be a term you're familiar with. Isosceles means that two of the sides on a triangle are the same. So that would be this one here. Scalene might be a word you've never heard before, though. Scalene means that none of the sides are equal to each other. It is this triangle down here where none of the sides are equal. It also helps that it says it's a right scalene triangle, so that means right angle on it. So that's what you're looking at there, is a right scalene triangle. Okay? So let's move forward here. What about an equal angular quadrilateral? Equal angular is the way we refer to the angles in an object. Okay? Equal angular means that all the angles are equal to each other. So there's only one down here that shows the angles being marked equal to each other, and it's this four-sided object down here. Amazingly, quad, Q-U-A-D, means four. So quadrilateral would be this four-sided object with all the angles equal to each other. Okay? Now, this next one says equilateral hexagon. Hexagon means 6. So you're looking for a six-sided object, and because it says equilateral, all the sides will be equal. See how the little marks on the sides of this one here indicate that they're all equal to each other? So that would be my equilateral six-sided object. The last one says heptagon. Hepta is a word you might not be familiar with. The prefix on that, that is the word for 7. If you look down here, this object has 7 sides on it, even though they're not, some of them are marked being equal, not all of them are marked being equal. So this is a heptagon, 7-sided object. Okay? So since we're talking about polygons, let's talk about symmetry. Symmetry is the concept that half of an object can be folded over the other half of the object, and everything lines up perfectly. If you look at this butterfly, the right side can be folded over on top of the left side, and it would be equal to each other. It'd be the same thing. So this wing here could be folded over on this wing here. You can see perfect symmetry right down this line here. So this line of symmetry is a line in which the butterfly could be folded, and it would line up, everything would line up on itself. Okay? When I say line up, I mean that one side fits on top of the other side. So it's like folding it in half and having all the corners meet. Okay? You do that with sheets and with towels and things like that. So if we look at geometric objects like this square over here, how many lines of symmetry are there? Well, you can see on this one, I've drawn some lines in here. These lines are dividing the object in half, and I folded on any one of those lines, the corners would match up. So how many of them are there? Well, there's a line going horizontally across, one diagonally and one vertically, and then another one going diagonally across. So I count 4 lines of symmetry there. It's not line segments, so it's not partial lines going from the center out. It is lines that go all the way across. So there are actually 4 lines of symmetry in a quadrilateral. In this square, equal angular, equilateral, or regular quadrilateral has 4 lines of symmetry. So this one over here, well, it's a quadrilateral, and it might be equilateral in which all the sides are equal, but there's only 4 lines of symmetry in it, rather than, or 2 lines of symmetry in it versus the 4 in this one. What's the difference between this one and this one? It's the fact that it's not equal angular. See how you could fold from this corner to this corner and it would still line up along the sides? I can't do that here. If I try to fold from this corner to this corner, it won't line up correctly because it would be off kilter a little bit, okay? Meaning not line up quite correct. It's because it's leaning off to the side this way. Push it that way. Yes, it's leaning that direction a little bit. So it doesn't quite line up correctly. So this one only has 2 lines of symmetry. Look at the poor triangle here. It only has 1 line of symmetry going through it. Okay? And that's because this corner could come to this corner and it would line up, but I couldn't take this corner and put it to this one and have it line up at all, could I? Not in any way, shape, or form. For this rectangle over here, yeah, I could fold it along the line here or along this line here, but if I fold it along the diagonal line that goes from this corner down to here, it wouldn't quite line up. My corners here would not line up with this corner over here. It would be out over here somewhere. So you don't have perfect symmetry in every direction on every object. The thing that you're going to find out is that if it's a regular object, like this one's a regular quadrilateral and this one's a regular triangle, then the number of sides tells you how many lines of symmetry there are. So a regular quadrilateral has 4 sides. It has 4 lines of symmetry. A regular triangle has 3 sides. It has 3 lines of symmetry. Now what was regular again? That meant all the sides and all the angles are equal to each other. So this one here, that one looks like a spider really badly. How many sides are on it? 1, 2, 3, 4, 5, 6, 7, 8 sides. I think all 8 sides are equal and all 8 angles are equal because I see 8 lines of symmetry there. So if it's a regular object, that means it has an equal number of sides and lines of symmetry. That's the way that works. Okay? So let's look at a couple of things here. Scalene triangle. Scalene triangle is not a regular object. All the sides are different. So the number of lines of symmetry in this one is none. Isosceles triangle. Isosceles triangle has 2 sides the same. This one actually has 1 line of symmetry. An equilateral triangle, that means all 3 sides are the same. It has 3 lines of symmetry. This trapezoid down here is quadrilateral. It doesn't have as many. It only has 2. I'm sorry. Is there 1? Yeah, 1 line of symmetry in that quadrilateral that's there, that parallelogram that you see there. Now you notice there's something else over here. It says degree of rotation. The degree of rotation is if I take this object and I try to twist it and turn it and move it around a circle like this. Okay, going around that way. Well, what you'll find out is the degree of rotation is measured in degrees. And what you're trying to do is see how many degrees it takes to make it so that it lines back up on top of itself. If it's a regular object that has the number of lines of symmetry, you can take 360 and divide it by the number of lines of symmetry by 4. 360 divided by 4. And what do we get when we do this? We get, what, 19? Not quite right. 360. 60. I get 60 degrees, don't I? Nah, I gotta take out my calculator. I can't do it. 360 divided by 4. Too old. I can't get through this. I get 90 degrees. 90 degrees. That means I would have to rotate it 90 degrees to get the lines of symmetry to be lining up on top of each other. And if I do that, what I'm going to get is, that's my degree of rotation. If I look at this triangle down here, 360 divided by 3. 360 divided by 3 gives me 120. I have to rotate it 120 degrees to get it to line up on top of itself. Okay? If I take my octagon over here, 360 divided by 8. And what am I going to get? I'm going to get 45 degrees. So how am I getting those? I'm dividing the 360 degrees, which is a full circle all the way around, and I'm dividing that by the number of lines of symmetry that are there. It's not the number of sides, it's the number of lines of symmetry. Well, those are the same in a regular object. Yes, but if it's not a regular object, you're still dividing by the number of lines of symmetry. Okay? So looking at this one, 360 divided by 0, that's not even defined. I can't even do that one. 360 divided by 1, I get 360. The only way that I could be able to divide that one out and get that to work out would be if it was all the way around. I could only turn it, I'd have to go all the way around to get that corners to line back up again. Equilateral, 360 divided by 3 is 120 degrees. That's the easy way of doing this one. Quadrilateral, 360 divided by 1 is 360 degrees of rotation. You see what I'm doing there? How about this one? Equal angular quadrilateral. That means it's got equal angles but not equal sides. So what am I looking at here? There's two lines of symmetry. The degree of rotation, 360 divided by 2 is 180 degrees. I would have to rotate it 180 degrees to get it to line up on itself. Regular. Regular is the word I'm looking for here. If it says it's a regular quadrilateral, like this one right here, that means it has 4 sides. That means it has 4 lines of symmetry. 360 divided by 4 is 90 degrees. I have to rotate it 90 degrees to make it line up on top of itself. Pentagon. Regular. Okay? If it's a regular pentagon, that means it has 5 lines of symmetry. And that means if I take 360 and divide it by 5, I get 72 degrees. So the degrees of rotation in this situation would be 72 degrees. Regular hexagon, 6 lines of symmetry. Regular hexagon. Hexagon, 6 sides of symmetry. 360 divided by 6, 60 degrees of rotation. Okay? What I'm going to tell you is that in the Unit 2, or Unit 3, Part 2, the Unit 3, Part 2, you will be given an object. You will be asked, how many lines of symmetry are there and how many degrees of rotation? It's real easy. It will be a regular object. All you've got to do is say, regular object has number of sides. If it has that many sides, that means it has that many lines of symmetry. How many degrees of rotation does it have? I take 360 divided by that number and I get this number. That's how many degrees of rotation it would take. That's what I'm looking for when you do that question, okay? Going on. The difference between concave and convex. If it caves in, it's concave. If it doesn't cave in, it's convex. So in this particular situation, you notice over here on this polygon, I'm drawing a line. I'm trying to draw a line between 2 points inside of that polygon, and I had to go outside of the polygon to get there because this one caves in. Okay? See how it caves in right here? Caved in. That means this one is a concave polygon. This one has no points like that, no place that I could draw a line like that, so it is a convex polygon. Okay? Final thing I'm going to tell you about here today is called the interior angle sum formula. Interior angle sum formula says that if you're looking at an object, you can probably get triangles out of that object. And all they're doing is drawing imaginary lines inside of the object, trying to get some triangles that are there. And what they know about triangles is that all the angles inside of a triangle add up to 180 degrees. So what they discovered was a little mathematical formula they could use. They can say the number of sides minus 2 times 180 tells you how many the angles add up to. And they're just getting that by dividing the object up into triangles. So in this particular case, this quadrilateral, they're taking 4 sides, minusing 2 from it. 4 minus 2, that's 2. 2 times 180 means it has 360 degrees. The angles add up to 360 degrees. This 5-sided object, 5 minus 2, that's 3. 3 times 180 is 540. So that means this pentagon here has a 540 degrees of angles on the inside of it. That's an easy formula to remember. You can get that one without any problem. So if you're given a problem like this triangle down here, we can see 3 angles in the triangle. All you would have to do is say the 3 angles minus 1. 3 minus 1, that's 2. 3 minus 2, that's 1. 1 times 180. The interior angles add up to 180 degrees. But what about the exterior angles, Mr. Green? The exterior angles are the ones that are outside of the triangle. Well, anytime you're looking at a polygon and it's a regular polygon, nope, regardless of the number of sides on the polygon, if it's a convex polygon, any convex polygon, if I add up the exterior angles, it's going to equal 360 degrees, no matter what kind of polygon it is. So, 2 formulas. Exterior, always 360. Interior, number of sides, minus 2 times 180. That's all you've got to do. So let's work a quick problem here to see what we got. Find the angles, the polygon angles in this sample problem. Okay? I got a cough. So, what are we going to do? First thing I'm going to do is they're all exterior angles that they're looking for here. I'm noting that this one is 90 degrees right here on the interior. I'm betting this one out here on the exterior is 90 degrees too, because it looks like a line and it comes straight across, and I know that one's going to be 90 degrees. So I'm only missing this one angle right down here. Well, I know all the angles add up to 360 because these are exterior angles. So I'm going to add up 70 plus 80 plus, supposed to have found an answer underneath there. That's nice that there wasn't an answer underneath there. Let's try that again. So I'm going to add up 70 plus 80 plus 50 plus x plus 90. Do you see how I just went around the triangle, around that object, adding up the angles? That's going to be equal to 360 degrees. Okay? Well, I got to whip out my handy dandy calculator here, and I'm going to do 70 plus 80 plus 50 plus 90, and you get 290. So just going from that, I get x plus 290 equals 360. Now that wasn't hard algebra, that was just collecting like terms. So I'm now going to subtract the 290 from both sides, so x plus 290 minus 290 is going to be equal to 360 minus 290. Okay, well 290 minus 290 is 0, so I'm going to have x is equal to 360 minus 290 is going to be equal to 70 degrees. I think I found what my x is equal to. I found that value. Woohoo! I found x. She wasn't missing after all. Okay, what I've been doing here is using this last one here. Formulating and testing conjectures about properties and attributes of polygons and their component parts based upon explorations and concrete models. Now, you guys will get in your class several little things to play with. Look at those in the lesson. You've got to play with them a little bit. Sometimes they will help you understand how symmetry works. They'll help you understand how many sides on a polygon work. They'll help you understand the difference between regular and convex and concave. Make certain you're doing all of them because they do help you. And then there's a couple of GeoGebra files that help you with figuring out the angle sum theorems. Okay? Okay, having done that, I think that's all I've got. Remember, if you're calling me, if you're sending me a K-mail, if you're sending me anything like that, make certain you include what course you're in. I've got lots of different courses and sections, and so by telling me what course and what section you're in, it really helps me find you and identify the problem a little bit quicker, and I would appreciate it. Thank you very much, and I'll see you next time.